Okay, everyone, welcome. Next up, we have Eylon from Bar-Ilan University. Take it away.
Okay, thank you. Hi. So first, this is joint work with my student Gal Arnon and Alessandro Chiesa and Giacomo Fenzi. And I'm kind of very excited to be here, and this is a kind of present WHIR. This is the premiere presentation of WHIR. Last ZK Summit, we presented the STIR, and this is kind of a new improvement on top of that. So WHIR is a Reed-Solomon proximity test, and it has super fast verification. And so I'm going to go slightly into technical details about that. And we're also going to see benchmarks. And yeah, so let's start. So first, we're in the ZK Summit conference, and what are our goals? We want to construct snarks. Okay, these are succinct, non-interactive arguments of knowledge. So we have a prover, we have a verifier. The prover wants to convince the verifier that he knows the solution, right? He knows a witness to this instance. And in our case, the prover and verifier are going to share something called a random oracle, as Anna discussed this morning. So they both have access to this random oracle, which they can query and get back a completely random answer. And we want the proof, of course, to be kind of very small, okay? In particular, much, much smaller than the size of the witness itself. Okay, so we're going to only have a random oracle. There's no other assumptions, okay, assumed in this talk. Once you have such a scheme, you can replace the random oracle with some concrete hash function. Okay, so you instantiate the random oracle with a hash function, and what you get is a snark that you can deploy in practice. And the advantages of such snarks are that they have a transparent setup. Okay, so the only setup that they require is choosing this hash function. They usually are quite highly efficient. So there's no public key crypto, there's no elliptic curves and stuff like that. There's only hash functions, and usually over small fields and stuff. And so they're quite highly, they're fast. And they're also post-quantum secure, if you care about that. Of course, today, these snarks are used to secure billions of dollars in blockchain transactions. I guess you know about this. This is just a small subset of the companies using this stuff today. Okay, so how do we construct hash-based snarks? What we do the following. We first construct an IOP. An IOP is an interactive proof between a prover and a verifier, where the verifier does this small number of queries to the proof. These are the green locations here. Then you take this proof and you compile it using something called the BCS transformation. Okay? Roughly speaking, every message of the IOP, you're going to Merkle tree. Okay? You're going to create a Merkle tree and commit to it. And then when the verifier wants to read something, you're going to send the authentication path. And all of these long rounds of interaction, you're going to use fiat shamir to compress to one message. Okay? And the efficiency of the snark is mainly determined by the efficiency of the IOP. So the prover is roughly the same. The verifier is roughly the same with additional hashes. And if you have some proof lengths of length L and Q queries, okay, usually the proof length is kind of big. This is the size of your computation, let's say 2 to the 24, and you have some number of queries. This is going to affect the argument size at the end and the verifier running time and so on. Okay, so we want to construct more and more efficient IOPs, okay, for the relation you want to prove for R1CS or something like that. How do we construct these IOPs? And this is the last slide before we go to STIR, to WHIR. What you do, you construct these polynomial IOPs. Okay? So a polynomial IOP is just an IOP where we restrict the honest and malicious prover to send only polynomials. Okay? So they have to send polynomials, and the verifier, what he can do, he can query these polynomials, he can evaluate them at any field element that he wants. Okay? So the prover is going to send some polynomial Q, and then the verifier can query this Q at some point X, and then you have maybe some polynomial P and Q and so on. And once we have this polynomial IOP, what we do, we compile it to a standard IOP. okay? That is then later going to go to the BCS transformation. And how do we compile these polynomial IOPs? What we do, we either use a polynomial commitment scheme, which is just a cryptographic way of enforcing the prover to really commit to a polynomial. But actually, more generally, I just want to take this slightly higher view as any compiler that takes a polynomial IOP and outputs an IOP. Okay, so one way to do it is using a polynomial commitment scheme and then doing this function by function, but any such compiler is what we want. And any such compiler is, in particular, actually a polynomial commitment scheme. Okay. We have many examples. Many of the snarks we know today use this blueprint to construct snarks. And there's many examples. I'm not going to name all of them. The polynomial commitment scheme that you use underneath could be KZG or something based on lattices or something like that. Or it could be something based on hash functions, so a hashed-based polynomial commitment scheme. And this is going to be the focus today. And I'm just giving a few examples. This could be Fry-based, or stir-based, or BaseFold-based. And these are the 3 examples I give because we're going to mainly compare to them because they're the most relevant to this work. OK. So the way these hash-based polynomial commitment scheme work, we ask the prover to kind of, instead of sending a polynomial, evaluate it at many points. And then we kind of need to test what the prover do. So this leads us to a result. So in this work, we introduce a new polynomial commitment scheme that has a really super fast verification. OK? So more technically, what we do, I need to define what the Reed-Solomon code is. So we recall what the Reed-Solomon code. We had some finite field F. Okay? We have some evaluation domain L. And we have some parameter M. M is going to be the degree. And then we're looking at the Reed-Solomon code. So these are all functions F from this domain L to the field. Okay? So all evaluations of functions, such that the function is univariate, low-degree polynomial of degree at most 2 to the m. Okay, so m is going to be log the degree in this example. So this is the Reed-Solomon code. And equivalently in this work, we kind of have this dual view of the Reed-Solomon code, where you can look at it as a univariate polynomial or a multilinear polynomial. So you can take the 2 to the m coefficients, and you can view them as coefficients to a univariate polynomial, okay, of the degree 2 to the m, or a multilinear polynomial, okay, that has m variables. Okay, so we have this duality between the two. Either we have m variables, or just one variable with degree 2 to the m. Okay, so what we do, we're going to define a constrained Reed-Solomon code. Okay, and this is going to be very helpful for us. And this will allow me to tell you exactly what WHIR is. So a constrained Reed-Solomon code is just a subset of the code words of Reed-Solomon that has this additional sum constraint. So this sumcheck like constraint that you add upon it. So my code now is not on all code words, okay, but just a subset that satisfies some additional constraints. So this W is going to be some polynomial, and sigma is some target sum. And then I'm looking at all the polynomials in the multilinear notation that satisfy this additional sum. And this additional sum in particular is expressive enough to express a constraint of an evaluation of this polynomial f. So I have f, and I want to say, oh, but f on some point z equals sigma. And there is a way to translate this to such a constraint. Okay? And this is what allows us to use WHIR as a polynomial commitment scheme. Okay. So what is WHIR? WHIR is an IOPP, an IOP of proximity, for constrained Reed-Solomon codes. Okay? Where Fry, if you know Fry is an IOPP for Reed-Solomon codes, and stir is also an IOPP for Reed-Solomon code. WHIR is going to be an IOPP for this constrained Reed-Solomon code. okay? Or in other words, in words of higher marketing words, it's a polynomial commitment scheme for either univariate or multilinear polynomials, okay? So it works for both. So for degree 2 to the m, okay, in the univariate case, or m variables with some security lambda and folding parameter 2 to the k, this folding parameter is some parameter, some trade-off that we can play with. It means that, like in the FRI protocol, in every query, you kind of read 2 to the k field elements, okay? The query complexity of WHIR is this expression. This is lambda over k times log m, okay? And forget about this complicated expression. We'll see it in a second, and we'll have benchmarks also soon. We kind of set k to be roughly log m, and then what you get is the query complexity is actually O of lambda, which is actually optimal. The verifier running time is this query complexity. Well, the verifier needs to do something per query, right? Times 2 to the k plus m. So again, 2 to the k is going to be the bigger term here. And for every query, the verifier reads 2 to the k field elements. This means that in terms of field operation, the verifier is actually linear in the number of field operation it reads from the proof. Okay? This is what makes the verifier very fast. And not only that, actually the verifier performs 0 divisions. Okay? So not divide by 0, but it doesn't perform any divisions. Okay, the alphabet is what I said. You read 2 to the k kind of field elements in every query. This is the rounded complexity. It's m over k, and the proof length is linear. Okay, so what does this mean? How does this compare to prior work? And what does it mean with actual numbers? Okay, so first let's compare the query complexity to some prior work. So BaseFold is a multilinear polynomial commitment scheme. The query complexity is lambda times m. FRI, if you know the FRI protocol, has query complexity lambda over k times m. So BaseFold just doesn't have this folding parameter built in, so it's kind of fixed to 1. STIR is a polynomial commitment scheme that we introduced last ZK summit that kind of improves the FRI, so you can see the improvement here. So the query complexity is lambda over k times log m instead of times m. So it gains a huge factor there. And WHIR just borrows the same query complexity as STIR. Okay, so it has like the small query complexity. Now, in terms of the running time, BaseFold is actually linear in the number of queries, so it's O of Q BaseFold. Okay, that's good, but it kind of has a lot of queries. FRI does this, has a running time, okay, this is the verifier running time, of O of Q FRI times k times 2 to the k. This makes a lot of sense because FRI needs to do like this small FFT of size 2 to the k for every query that it reads. And so this k 2 to the k is just the time of an FFT of size 2 to the k. Okay? STIR has this slightly even worse running time, okay, has this plus lambda square, okay, which sometimes is actually, could be quite big. And the running time of our verifier is actually Q WHIR, which is the smallest query complexity, times 2 to the k plus m. Okay, so we even shave out this factor k. Okay, now it's really linear in the number of queries and not quasi-linear. Okay. So now benchmark and implementation. So we did implement this scheme, okay? Kind of academic level implementation, not industry level implementation. We implemented using Rust. We used the artworks as a backend. We took an extension field of the Goldilocks field. I really want to thank Remco for helping us, Remco from WorldCoin for helping us with like optimization of the prover and verifier. What the benchmark you're going to see today are like partially parallelized, so there's a lot of room for improvement for the prover running time if you have a lot of CPUs. And we compared it with FRI and STIR and BaseFold as a polynomial commitment scheme. So let me tell you about the results. So let's start. So the WHIR verifier typically runs in a few hundred microseconds, okay? Other verifiers even those that have a trusted setup, KZG and other, usually take several milliseconds, if not more. Okay? And we do this without like compromising or without some bad trade-off between the running time of the prover and the argument size. Okay, so it's like a true improvement and not a trade-off. As an example, okay, as a polynomial commitment scheme for degree 2 to the 22, you can think of this as like roughly equivalent to 4 million constraints. With 100 bits of security, I ran this last week on my laptop. I have a MacBook Air. The prover time took roughly 1 second. The commit and open together were roughly 60 kilobytes, okay? And the verifier time to verify this opening was 207 microseconds, so roughly 1/5 of a millisecond. Okay, so this extremely fast verification, sorry, here's a slightly more comparison with other schemes. So we have KZG here, and Ligero, and Breakdown, and Hyrax, and you can see the numbers. So usually these numbers are either large or a few milliseconds, where WHIR is the only one, depending on parameters, kind of go below the millisecond barrier. Okay, once you have such a fast verifier, you can kind of think of new applications that open or improve. So I just want to really, sketch two things that I think are interesting. So first is on-chain verification. And all of these are kind of, this is the back-of-envelope computations that we did. And, to get exact numbers, you have to really implement this and see exactly how much you get. But today, we verify Groth 16 proofs, okay, on-chain over the BN254 curve. And this takes roughly 280K gas, okay? Possibly, one future is where we use WHIR to verify this stuff over smaller fields. And kind of some estimates that we did said if you take a degree 2 to the 22, you're going to get roughly 50K gas, okay? And even if you go up to degree 2 to the 60, 2 to the 26, this should be 80K gas. Okay, so this could be a big improvement in the gas cost of verifying proofs. Okay. Second, of course, is the recursive verification. So if you use WHIR as the first step, in a recursion, in the second step, the prover is going to run and prove the code of the verifier. And here we did another set of computation. So here we went for 128 bits of security with degree 2 to the 28, so kind of a large computation. Then because the query complexity of WHIR is small and the verifier is fast, kind of what the WHIR verifier is going to do is roughly 3.4K hashes. Okay, this is to verify the Merkle tree hashes. And if you kind of assume that this hash is Poseidon, or most of it is Poseidon, which is roughly 400 R1CS constraints, then you're going to get that the recursive circuit, okay, that you need to prove is of size 2 to the 20. Okay, so you start with a computation of size 2 to the 28, okay, and then you run one WHIR iteration, okay, and the next step you have something of size 2 to the 20, and then you can, much smaller computation, and everything is much faster, and you can run whatever you want. Okay. Comparison. So here's a comparison to BaseFold. I want to be fair and say first that we are inspired by Fry and BaseFold and Steer, and kind of this work accumulates many ideas and new ones from all these works. And also that, to my best of understanding, these numbers from the BaseFold paper are kind of not optimized in the most significant way, and probably can be better. But okay, let's see how we compare. So red is BaseFold. In blue, we have WHIR UD, which is the unique decoding radius. This is kind of without any conjectures. And in green, we have this WHIR capacity bound. So this is with this list decoding type conjecture that is not the same, but kind of similar to what happens in Fry and Steer and all these kind of schemes. So we start with the argument size. You can see that the BaseFold argument size is kind of very big compared to both the WHIR unique decoding and capacity bound. Okay, so even for quite large computations, the argument size really is less than 100 kilobytes. The prover time, you see, so we didn't compromise in prover time, so the prover time is roughly the same as BaseFold. Here it's slightly better, but I imagine you can also improve the BaseFold prover, okay, to make it better, and you can also improve the WHIR prover to make it better, and so this is a kind of a competition. But for the verifier runtime, there's kind of, there's not a lot to improve. It's kind of a small piece of code, which is usually kind of optimal, and that's just what you get. And so you can see that both versions of WHIR are kind of nearly the 1 millisecond, sometimes below, maybe sometimes above if you don't assume the conjecture, while the BaseFold one is kind of high, around 20 milliseconds. Let's compare if you are familiar with FI and STIR. Maybe I'll say at this point that WHIR is a drop-in replacement to places where you use FI or STIR or BaseFold as a polynomial commitment scheme. Okay. So again, if I compare that, we can see that, so STIR, what we introduced last ZK summit, okay, is in blue now, and in red is FRI. So the argument size is much better than FRI. That was the main point of STIR, and WHIR just gets roughly the same argument size. The prover time, you can see, is roughly the same in all schemes. Okay, mainly the bottleneck of all these schemes is to do some big FFT, and this is kind of what they do anyway. The verifier hash complexity is much smaller in STIR and WHIR. Okay, but in WHIR also the field operations complexity is much smaller. So you can see here, okay, so the green one is WHIR, okay, and both STIR and FI have like a much larger verifier time. Okay, how am I on time? I have. Okay, so a little more results. Okay, so because WHIR was not just a Reed-Solomon proximity test, but actually a constrained Reed-Solomon proximity test, what we can do with it, we can compile not just a polynomial commitment scheme, but actually this sumcheck polynomial commitment scheme, or as I denoted here, just a sigma IOP. So a sigma IOP is going to be like a polynomial commitment scheme where I force the prover to send polynomials. Okay. Here, I'm going to allow the verifier not just to do evaluation queries to this polynomial, but actually sumcheck queries to this polynomial. Okay, so the verifier can specify a polynomial W, okay, this weight polynomial W, and he can get back this answer sigma, which is this sum. Okay, so he can kind of do a sumcheck-like query to these polynomials that the prover specifies. Once you have this power, then a lot of the effort is reduced from the polynomial IOP itself, okay, because the verifier is much more powerful. And all of this is encapsulated anyway into the WHIR low degree test that we run. And so what we do, we actually give a sigma IOP for generalized R1CS, which is kind of has much more efficiency than other polynomial IOPs that you get. And all of this is compiled and batched together to one WHIR invocation at the end for some polynomial and for some constraint, okay, that kind of is a combination of all the constraints that the verifier queried. Okay, so this gives an efficient way to go from ROCS to IOPs. We kind of didn't implement this yet, and so I don't have really like benchmarks for this part. Yeah, okay. So I think I have just one more minute, so we have something new called mutually correlated agreement. I have just a quick minute on that. So kind of the main technical tool that we use is this proximity gaps, which roughly says the following. Oh, I have many evaluations of functions, okay? And I don't want to test each one individually, so I'm going to take a random linear combination of them. So I have C1 up to CL, and I have the C star. And I have this theorem by Ben-Sasson et al., okay, in this proximity gaps paper, and also Dan Carmon, this should be here in the conference, saying that if the C star is close to Reed-Solomon with high probability, then all the CIs were actually also close to Reed-Solomon. So you see C star, the green spots, it's where it's close to Reed-Solomon, and every CI also has to be close to Reed-Solomon. But actually what they proved is something much stronger. They proved something called correlated agreement, okay? So they proved that this is not the right picture. Actually, all the CIs are going to have a correlated agreement. They're going to agree with Reed-Solomon at the same domain, okay? So the picture is not like this, but actually like this. Okay, so all the CIs, not only that they agree with Reed-Solomon, but they have some shared domain where on it they agree with Reed-Solomon. And kind of what we do, we introduce these new proximity gaps, where we say that it's not enough that the CIs have shared correlate agreement, but the C star should share the same domain as well. Okay? So the picture should be like this, where C star and all the CIs have, so we call this mutually correlated agreement. So we prove that any time you have correlated agreement, you have mutually correlated agreement up to the unique decoding radius, and we kind of still leave it as an open problem to prove it beyond. Okay, conclusion, we introduced WHIR. WHIR is an IOPP for constrained Reed-Solomon codes. I think it can have other applications, but the main one is, of course, using it as a polynomial commitment scheme. We have verification time within milliseconds, prover time within seconds, and the proof size is really tens of kilobytes. We introduced this new mutually correlated agreement proximity gap. We have this sigma IOP, where we combine it with our WHIR, okay, and then you apply the BCS transformation, and all of this together gives you our hash-based SNARG. This fast verifier can gain new applications such as, efficient on-chain verification, recursion, and other stuff. Yeah, that's it. Thank you.
Okay. Do we have any questions in the audience? Question. This is where I get my cardio in.
So surely I'm just not understanding something. I'm trying to understand why this mutual correlated agreement doesn't follow for free from correlated agreement. Can't you, in other words, assuming that the CIs have correlated agreement on some domain, can you not always just take the underlying code words, combine those in the same way, and then you get the same error domain for the C star? Why does that not come for free?
Yeah, good, excellent question. So you're right. So the CIs have correlated agreement, which means that C star at that same domain, which also be close to the code word. But what I don't get as a guarantee from the proximity gaps paper is that C star might have additional domain, which is close to the Reed-Solomon code, where the CIs do not agree on that domain. Okay, so I want every place that C star agrees with the Reed-Solomon, the CIs have correlated agreement on that domain.
I see. So that needs to be the only domain
It could be more than one. Could be more than one.
But then the others have to also be close.
Yeah. If C star has 10 domains where it's close, that's fine. But all the CIs also have 10.
They need it too. Okay.
Okay. It's kind of an if and only if.
Got it.
Okay. Thanks. That was a great question.
Any other questions? Okay. Round of applause for Eylon.